In this course module, I want to have a bit of a talk about a question that I see asked all the time on social media around modifying street cars and building club level race cars. So we've got a bit of a theory example here, and we're going to think about modifying a vehicle from possibly the 80s, 90s, even into the 2000s, and modifying that to maintain being a street car but also be a club level race car. Now the question I see asked over and over is, hey, I want to pull every wire that is in this vehicle out. What's the minimum amount of stuff that I need to put back in to keep that vehicle a nice street car and a club level race car with maybe just a little bit of usability retained in there as well? So I've put together a bit of a list of what I think to be the minimum viable solution to this problem. Now this is going to have no legal bearing. It could be totally different in your part of the world in regards to what sort of lighting and fixtures your vehicle needs on it. So absolutely make sure that you're looking that up for where you live. But if we're thinking about a club level track car, that's going to be less restricted by laws. So I think a solution like I've put together here is actually going to be a really good option. So we're going to look at this from the standpoint of we've removed every wire from the vehicle and we want to replace all of the original fuses and relays in that power distribution system with a PMU, and we'll talk about how that PMU is going to make this as easy as possible for us. So the first thing we'll do is we'll pop over to my laptop and we'll just have a look at a bit of a list I've generated here. So this is just a pure theory example here of some possible devices that might be running our vehicle. Now, thinking of modified street cars, track cars, chances are it's going to be fuel injected. So we're going to have an ECU, and ignition system might comprise of individual coil per cylinder. That's a good way to go. Injectors, alternator, control of the starter motor is really nice to have, fuel pump and a cooling fan. So to run an engine, that is pretty much going to be the minimum viable solution that you're going to need. Engines need fuel at about the right time, they need spark at really very much the right time, and they need some compression. So from those items there, we're going to be able to give the engine all of that and we're going to be able to run it quite nicely. Now this is just the power distribution side of the equation. There are obviously going to be sensors that the ECU is going to need fitted to it, that are fitted to the engine to get data on coolant temps, throttle position and stuff like that. But those sensors are powered by the ECU. So that's a reasonably separate subject that we have got covered in other places. Talking about the power distribution, the power management side of things, we just need to think about how we're going to supply power to those 12-volt devices. So I've got some proposed current draws for our examples here. Just good to keep in mind, these could be reasonably generic values that you could use if you're sizing up a project like this yourself and you want to specify a PMU for that project, just to make sure it's going to have enough channels and current handling capability for what you want to do. So ECU, I've said, is going to draw around about 10 amps. Now, different ECUs are really different in the amount of current they draw, and if they're actually having to power any 12-volt devices themselves, like throttle plates or anything like that, then their current draw is going to be quite different. So that's a little bit on the higher end of the scale of what I'd be expecting an ECU to draw, but it's sort of just a catch-all to cover all of that, because this is just for specification purposes. Coils, I've said, are going to draw about 10 amps consistent. Once again, that's at the upper end of that scale. Injectors, 5 amps. Alternator field winding, we could expect to be about 5 amps. Starter solenoid, obviously really different for every engine again, but 15 amps on that one with a big inrush of 50 amps. Fuel pump, 9, 10, 12 amps. They're in around about that zone for an electric fuel pump. We wouldn't be talking about a massively high performance vehicle here requiring a huge fuel flow at pressure. So we'll be going with a single fuel pump there, drawing around about that current range. And we want to have a PMU controlled or an ECU controlled cooling fan on the system as well, because that's going to get us away from needing to use discrete temperature switches and things like that. So a current draw of, once again, around about 9 amps, big inrush current on those, about 50 amps. So now that's a reasonably well-trodden path. You'll be able to find that information in a lot of places, but where people tend to stumble a little bit is thinking about the rest of the elements in the vehicle and the things that might be really necessary for your modified street car or out there on the racetrack. So lights. Lights are actually a really big current draw part of a vehicle. I don't know if it's often realized how much current the lighting in the vehicle actually draws, but this is why you'll notice when you go to start your car, often your headlights, park lights, and things like that will actually turn off. So that's the way the vehicle has been wired, and its power distribution system, its OEM one, will turn those high draw devices off while the starter motor is cranking, just to be a little bit easier on the battery. Now, of course, that's functionality that we can implement with our PMU as well. So looking at our lights here, first up we've got our park lights. So pretty common for a vehicle to have park lights, or I want to stay away from the word indicator in this instance, but signal lights on the front and the rear, at each corner, around about 5-watt bulbs. So often when you turn your lights to the first stage, your headlights actually don't come on, but these sort of indication lights will. So we've set a current draw there of around about 2 amps. And the way we've landed on that figure is we've looked at the fact that we've got 4 5-watt bulbs. Now a 5-watt bulb, we can work out its current draw because it's 5 watts of power. Power is voltage times current. We're going to make an assumption when we do all this math that we're working with a 12-volt system. So if we've got a 5-watt bulb, well, round that up to 6 watts to make the math easy. I can take 6, divide it by 12, and I'm going to get 0.5. So 4 times 0.5 is a 2 amp draw. So working down our list, we've got our dip headlights here. So often vehicles of this era are going to have halogen headlight housings with, we'll say, H4 halogen headlight bulbs. So they're a twin filament bulb, often called a 6055. So they've got a 55-watt filament and a 60-watt filament. Typically the 55-watt filament is for the dip beams and the 60-watt filament is for the high beams. They're in slightly different places and they reflect light in a slightly different way. There's an actual internal reflector in that bulb. Now, one thing about halogen bulbs like this is you never want to power both of those filaments at one time. You're going to overheat that bulb and cook it really quickly. So you'll find in every factory implementation like this, when you flick the high beams from high to low, it's going to change which filament is being powered. It's never going to power both at the same time. So once again, we can work through our math there and we come up with around about a 10 amp draw for those headlights. Obviously, there's only going to be one of those draws at a time, but we are going to need 2 individual channels because we can't run them both at the same time. So headlights are a pretty decent draw in a vehicle. Indicators left and right. So it'd be common to have a 21-watt bulb for an indicator at each corner of the vehicle and a 5-watt bulb maybe on the side guard, depending on where you are in the world. You might not have those. So we've got a current draw of approximately 3 amps per indicator channel, being one channel being left and one channel being right. Brake lights. Brake lights can be another pretty decent draw because most vehicles have they'll have 2 21-watt bulbs at either side of the rear of the car, so it's 4 in total. 21-watt bulbs draw around about 2 amps each, so that's 4 amps per side, so 8 amps in total. And then often there's a center stop light as well. So the the vehicle I was thinking about when I wrote this list was actually an FD RX-7, reasonably predictably. And that has 4 21-watt bulbs for the brake lights and 3 18-watt bulbs for a center stop light. So we've said I've got a current draw there of about 13 amps when all those brake lights are at their highest brightness. Reverse lights, pretty common, 2 21-watt bulbs down in the bumper there, so we've got a 4 amp draw on those, and a license plate lamp, just a 1 amp draw on those. They're often 5-watt bulbs. Now, obviously for a club level race car, license plate lamp is not going to be important at all. Probably pretty important for a modified street car though. I've included it in there because you'll see when we get to designing the control functions for this example that the driving functionality for that is exactly the same as for our park lights. So it's not going to cost us any extra channels to have those in there. A little bit of extra wiring to the back of the vehicle, but no great drama there. Another key element we're going to need on our vehicle are windscreen wipers. So windscreen wipers are a key safety element. You absolutely are going to need them on a modified street car or a track car. A lot of race classes won't actually successfully get your car through scrutineering if it doesn't have functioning windscreen wipers. So we've gone through windscreen wiper operation in a bit of detail in the course. So this is exactly the same scenario we're talking about here. We've got a 5-wire windscreen wiper motor with a low and a high speed. Low amp draw is around about 2 amps. High speed draw is around about 6 amps. I'm going to include the window washer pump in this as well, because I think window washer squirters are actually really important. Where we are here in Queenstown in New Zealand, it is really dusty, and every morning you come out and your windscreen is covered in dust, and it causes a lot of glare, and if that gets just a little bit damp from some mist or something like that, it can really impair visibility a lot. So window washer pump I consider to be a pretty crucial item for the front windscreen there. Not a massive current draw on those, pretty low power items, so we've said that's 2 amps there. A horn is another critical safety element for particularly a modified street car, but actually can come in handy for a club level race car as well. Horns have a higher current draw than you would expect. If you look at the factory wiring to a horn and the factory fuse rating on that, you'll find they're normally run on a 15 amp fuse. If there's 2 horns in the vehicle, you might be getting up to a 20 amp fuse as well. Pretty high current draw. So we've said 5 amps on that one with a limit of 10 amps. So running through that list there, that's the minimum viable number of elements that I would want to put back into a pretty bare bones stripped down modified street car or a club level race car. So the kind of things I'm thinking about here would be maybe a rear wheel drive Toyota Corolla from the 80s, something cool like that you're putting a later model engine into, and you want to strip all the wiring out and just start from scratch. So that sort of really bare bones resto mod project, this information is absolutely going to be applicable for. So we've talked about the elements the minimum viable number of elements that we're going to need. Let's have a talk about what's going to control those elements. So these are going to be the inputs that we're going to put into the PMU that are going to run through our functions and decide how all those outputs are switched on and off. So switching back to our laptop here, I have got some control functions defined. So if we look at the first 4 elements here, ECU, coils, injectors, and our alternator, they're all going to have the same driving control function. And that is going to be our ignition switch in the on position. Now, we'll talk about this in a wee minute because I'm going to go through some factory documentation to show how to read that, to decipher how the OEM switches and such in the car work so we can interface those with our PMU. But something about ignition switches that I'm not going to say it's not well known, but sometimes it trips people up, is that they've got multiple outputs for different stages. So the accessory, the on, and the start position. That's probably not a surprise to anyone, but there's probably 2 different outputs for the on position. And when you flick it to start, one of those will actually be disabled and the other will stay on. So that's for turning off loads when the engine is being cranked to make the engine crank faster and be kinder to the battery. But we want to make sure that things like, well, our system critical elements like our ECU, coils, injectors, and our alternator remain powered while we're cranking the engine. So actually, we'll just pop over to our factory documentation here. So I've got a factory service manual for the FD RX-7 open here, and I've got it open to a page that shows our ignition switch. And I just want to have a quick talk about how we actually read this diagram. So you can see here we've got a central input point for our power coming into the system. So if we just scroll out a wee bit, this is our battery through a couple of different fusible links, and this is going to get our power input to our ignition switch. So in our modified car example, we'd probably be replacing those fusible links with some sort of battery isolator system. And then we'd put that power into our ignition switch on the output side of that isolator. So the way to read this diagram is we look at our input stud here, and in the off position, these 2 points are making a connection. And then as we turn the ignition switch, we rotate it through its different modes, this arrow here is rotated around and makes different connection points. So when we turn the ignition switch to the accessory point, it's going to make a connection between our input stud and our accessory output stud. Now on this particular page of the service manual here, there's nothing on this page that relates to the accessory power mode, which is why there's no wire shown coming off here, but there absolutely are things powered by the accessory mode in the vehicle. The radio being a key one that comes to mind in a factory setup. Now, there is a link between this accessory pin here and our on power mode here. So if we were then to rotate the key around one more click, that's going to get us to our on power mode. That's going to connect our input down through these 4 connections here. Now this connection back to our accessory, what that means is that when our ignition is in the on position, our accessory position is also powered. So you wouldn't want it the case of you flick your ignition barrel around to the accessory position, your radio comes on, that's great. You flick it to the on position and your radio turns off. So wouldn't be what we're after. So once we get past the accessory position, that remains powered in the on position. Now exactly the same thing happens when we flick the ignition to the start position. So this is often the sprung loaded part of the ignition key barrel. So we can see that would be connecting this point to our start terminal here. Now this is actually the charging and starting diagram, so it is going to show relay and the control logic that'll run through to our starter motor here. This is all the stuff that we'll be replacing with our PMU to keep things as simple as possible. So if we're in our start mode here, we can think of our input stud being connected to our starter motor. It's going to be to this output terminal as well. And it's also going to make a connection back to our on terminal. So the way this works is when we're in the on position, that's connecting our input stud to this stud, which is coming up here and making a connection through to all our engine electronics, because this is a 15 amp engine fuse. When we're in the start position, that connection is still being made. So you could think of this stud down here as being the on stud of the vehicle that actually gets disabled when we flick over to the start mode, whereas this stud here is the on stud that remains active. So we'd want to be absolutely clear we're wiring that up to the correct place. Now this is a pretty easy thing to test with a multimeter, particularly if you've got a factory service manual like this, because we can look at the wiring colors here and we can simply get our ignition barrel, we've got our wiring colors, it would be our X03 connector in this instance. We'd be able to probe the pins of that and make sure that everything is making a connection there as we expect. So hopefully that's going to help you read a factory service manual. If we head back to our logic here, we can see I've defined the control function for these elements here to be our ignition switch, start plus on. So that is that stud that is the on, comes on with the key barrel in the on position, but remains on when we turn it to the start position as well. Next up, we've got our starter solenoid. So that is obviously going to only be active when we've got that ignition barrel in the start position. Fuel pump and cooling fans, those are going to be ECU requests. So we've got our ECU powered, it's going to be reading sensors. It's going to know when it wants the fuel pumps to run because the engine's trying to start and it's seeing an engine speed signal. And cooling fans in response to the output from the engine coolant temperature sensor. So we're not going to use any, in this theoretical example, any CAN bus communications, although that actually wouldn't be particularly tricky to set up at all. We're going to think about those being discrete digital inputs from the ECU back to the PMU. Now any PMU out there is going to have multiple digital inputs. We've only got a couple listed here, so we're going to have more than enough. Now heading down to our lighting part of our example here, control function defined as ignition switch on and combination switch TNS output. TNS output is just Mazda's nomenclature for the lighting output mode that runs the park lights in the vehicle. So this is a similar situation to an ignition switch actually. So this is when you first click those lights on, that enables the TNS output. And then when you flick the lights to the next mode, whether low or high beam, that output remains on as well. So the park lights are being run as well as the main headlights. So when I'm talking about the combination switch here, we'll just clarify what that is. So a combination switch is the switch that's, or the switch cluster that's going to be directly behind your steering wheel. So pretty typical on most of the era of vehicles that we're talking about. Going to have an indicator stalk, going to be responsible for turning on the lights, and more than likely the wipers as well. So that's definitely a case of you're wanting to get the factory documentation for your vehicle if possible, because that's going to allow you to decipher the outputs from that combination switch. And I don't know, they're normally pretty reliable, they're nice, as long as they're in good condition. If they're falling apart, I'd suggest you probably replace them with a CAN keypad or something like that. But if they're in good nick, they're pretty reliable and robust, and they're a really good way of getting a lot of switched inputs into a PMU quite nice and tidily. So moving down our list here, we've got our dip and full beam headlights. So those are going to be our next lighting mode, and probably a pull or a push of the stalk as well. So what you get by using the combination switch is actually, it's still performing some of the logic around how our outputs from our PMU are going to be switched on and off. So it's got a momentary pull function for the flash to pass, and an on and off push function for just turning the high beams on long term. You'd be able to do something similar with a CAN keypad and set up some logic around that working, but it's already in that combination switch for you. So they are a really nice way to go if you can get them working. Got our indicators left and right. So those are obviously going to be combination switch again, but we're going to have a hazard switch on the vehicle as well. So what you're going to be able to do, particularly with a PMU here, is because that combination switch is now just going to be providing low-level inputs to the PMU can control all the switching of those indicators on and off. So you'll be able to define the indicator repeating period, and it'll be able to look for a hazard input as well, and simply flash all the indicators as opposed to just one side. So that does away with a flasher relay and a hazard relay as well. So really good to get rid of those elements out of the setup. Got our brake lights here as well. So that's going to be an input coming into the PMU based on a brake light switch. So brake light switches commonly mounted to the pedal boxes. Typically you call them normally off, because when the brake pedal is all the way released, it's pushing on that switch, which is turning that switch off. When you push the brake pedal down, it releases the plunger on that switch and actually turns them on. So chances are we'd wire that in with a pull-up, we'd wire it to ground on one side, wire it to the PMU on the other, and put a pull-up resistor on that, and that would get us a reliable input there. Reverse lights, very similar situation, but there'll be a reverse light switch usually on the gearbox, just engaged by probably the reverse selector shaft there. And license plate lamps, as we mentioned, exactly the same control functionality as our park switch, so just coming on when we're in that first lighting mode there. Now you'll see here for all of these lighting elements, I've got an AND function for their control element and our ignition switch on, except for the brake light switch. The brake lights are purely controlled by the brake light switch. So for any of these elements here, the ignition switch has to be in the on position, but not the start and on position. So when we go to start the vehicle, it is going to turn off all of these outputs, no matter what switches we have flicked on that combination cluster. They're going to be turned off, except for our brake lights, because brake lights are really important to work all the time, because if the engine stalls and you've got to turn it off and turn it back on, you might need to keep your foot on the brake to warn oncoming traffic that, hey, there's a car here and it's stationary. So important there. Now we're on to our wipers, once again controlled via low-level inputs from our combination switch. We've gone through a pretty detailed example of that in the wiper control module of the course material, so that would be exactly that setup there, except we're taking the inputs from the combination switch as opposed to a discrete separate switch. Washer pump will also typically be on that combination switch, and the horn is usually going to be just in the center of the steering wheel. So usually a horn button will switch to ground when you press it. So once again, we'd have a pull-up on the PMU input channel, and when we press that horn button, it'll switch it to ground, tell the PMU that we want the horn to be activated. So hopefully that's a good introduction to the minimum viable solution to the problem of I've ripped everything out of my modified street car, club level race car. I want to know what I need to put back in to have that thing driving, and maybe just a couple of creature comforts as well. Now, I'll definitely link this spreadsheet below this module, and I really encourage you to jump into the forums and have a discussion with us around this. If there's anything you think we've missed that we need to pop in there, or anything that you think is not essential, or how we could control things differently, I'd really love to hear about that. That was just one of the 36 modules taken from the PMU configuration course. If you want rock-solid, reliable electronics and advanced functionality that will help you win races, then this course is perfect for you. You'll learn about the fundamentals of power supply design for the electronics in your project and how to classify an electrical load to determine the correct way of powering it on and off. You'll learn about what a PMU is and how one can both simplify your power supply and wiring harness design, but give you a lot more flexibility to cater for future modifications. You'll learn about the basic logical building blocks PMUs use and how these can be chained together to build up advanced control functions that make our cars easier to live with, safer, and faster. You'll start with the basics of power supply design and build on this knowledge with the course, working towards specifying a PMU for a project and making sure you're getting the absolute most out of the technology. If you're thinking of using a PMU in your project, but are either on the fence about whether one will be suitable or intimidated by the configuration process, this course is for you. For more information and to purchase this course, click the link to enroll now.